we're given another example to solve for our reactionary forces on a bridge. And this example might look a little scary because it has two forces of gravity instead of one, but as we'll see, it's really not that much more complicated. So let's go ahead and start by labeling our reactionary forces. We have one at our roller joint going perpendicular, and we have, well, let me pick a new color for it. But we have one going perpendicular at our pin joint, and we have one parallel at our pin joint. And let's call this parallel one. Well, it's going in the x direction. It's a reactionary force at pin A at the x direction. And let's call this upward force, this reactionary force at point A in the y direction. And so Rax and Ray, and then we have a reactionary force at point D in the y direction, which we can call Rudy. And these are the three reactionary forces we're asked to find. So let's start, just like we did before, with the sum of all forces in the x direction. We know all the forces have to add up to 0. And if we look, there's only one force going in the x direction. And that's clearly Rax, which is going to the right. And since there's only one force going in the x direction, and we know all of our forces in the x direction have to add up to 0, then we know Rax has to equal 0. And that fast, we're already a third of the way done. Next, we need to look at the sum of all forces in the y direction. Well, that also has to equal 0. And we have two forces, or two reactionary forces in the y directions. We've got Ray and Rudy. And we got two forces of gravity going down, which are also in the y direction, so 350 pounds at point B. And then we have 250 pounds at point C going downward. And we can simplify this statement even further by labeling our upward and downward forces and realizing that our upward forces have to cancel out our downward forces to equal 0. So what does this mean? Well, it means Ray plus Rudy have to add up to our downward forces or else everything is collapsing. So Ray and Rudy equals 350 pounds going down plus 250 pounds going down. So Ray and Rudy have to be equal to the same amount going upwards, or else the bridge would be collapsing. And 350 plus 250 is 600 pounds. And if you look at this equation, we really don't have enough information to solve for Ray or Rudy. There's too many variables, so we have to go a different route. And that route is the sum of all moments also equals 0. Well, what are all my moments? If we look, a moment requires a force and a distance. Well, we have a force here at point B, and we have a distance from our pin. So it has a moment, and if you look, it's going downward. The force is going downward, and it's got to go towards our pin. It's got to rotate towards our pin, which makes it going clockwise. And we'll call this moment B, since it's a moment at point B. And we have another moment here at point C because we have some distance and we have some force. And so that moment is also going downward and then towards our pin, which is also clockwise, and we'll call this one moment C. And lastly, we have a moment because we have a force and a distance at point D. So it's going up since the force is going up, and it's still going to go towards our pin. And if you look at that, well, that's counterclockwise. And since it's at point D, we'll call that moment D. And you might say, well, what about moment A? Is there a moment at pin A? And I'll take this moment to remind you that there are no moments at our pin because there's no distance from our pin to our pin, so the moment will equal 0. And so now we can say, well, what are our moments? Well, we got moment B combined with moment C. And those two will combine with moment D to give you 0. And we can simplify this statement even further. To say that they equal 0 means our clockwise and our counterclockwise moments have to cancel out. Our positive moments have to cancel out our negative moments to add up to 0. Or else our bridge will be flipping over. So we can rewrite the statement to say moment B plus moment C add up. Well, they add up to moment D to cancel out. So what is moment B? Well, it's a force times a distance. Well, its force is 350 pounds multiplied by its distance from the pin. Well, it's 20 feet from the pin. And we can add that to moment C, which is also a force times a distance, and its force is 250 pounds multiplied by its distance from the pin, and you might be tempted to say 60 feet, but it's really not 60 feet from the pin. It's 60 feet and 20 feet, so it's 80 feet from the pin. And I moved this over a little bit just to give myself a little bit more room to work. But that's equal to moment D, which is a force which we don't know yet, and that's kind of the point we're trying to solve for this force of Rudy, multiplied by its distance from the pin, which is 100 feet from the pin. Well, we can simplify moment B by typing it into our handy-dandy calculator. So we say 350 times 20, and we get a moment of 7,000. And so we rewrite moment B as 7,000 foot-pounds. And we add that to moment C, which we can also simplify by saying 250 times 80 feet. And we get 20,000 foot-pounds, and we combine those two moments to equal moment D, which we labeled Rudy times 100 feet. And then we can simplify this further, because 20,000 plus 7,000 equals 27,000. Equals moment D, which we're labeling as Rudy, and that's kind of the point, times 100. And it's the point because we don't really care what moment D equals, we care what Rudy equals. But we need to define it to solve for Rudy. So we divide by 100 feet on both sides. And 100 feet cancel out, and then we get feet cancel out, and we do 27,000, I'm sorry, 27,000 divided by 100. And we get Rudy equals 270 pounds, which we solve from this equation. Well, really, all we have left to solve for is Ray, which we have all we need to solve for. We already know Ray plus Rudy equals 600. And we just solve for Rudy is 270 pounds. And so we can say Ray plus Rudy equals 600 pounds. And so to solve for Ray, we'll just subtract 270 pounds on both sides. And Rudy cancels out on the left, and we're left with Ray equals 330 pounds, which is our last reactionary force and the last part of our answer.